Example M4.3, the baggage truck A shown has a weight of 900 pounds and tows a 550 pound cart B and a 325 pound cart C. For a short time, the driving frictional force developed at the wheels of the truck is 40 pounds, where T is in seconds. So it's a function of time, and therefore it's not constant. If the truck starts from rest, determine its speed in 2 seconds. Also, what is the horizontal force acting on the coupling between the truck and cart B at this instant? So there's a coupling here holding cart A and cart B together. Okay, so neglect the size of the truck and its carts. So we will draw out the free body diagram. From that free body diagram, use the equations of motion, and then since we are supposed to look for the speed, we have to apply the kinematic equations. But as said in the module, you can idealize a system of particles, since this is ideally a system of particles, as one single particle when you apply the equations of motion. So we draw out the free body diagram, which has already been drawn out here. And it is the frictional driving force that gives both the trucks and carts an acceleration. Here we have considered all three vehicles as a single system. So since motion is going in the x direction, therefore we should introduce the frictional forces here. I'm not even sure if there are frictional since there is no frictional coefficient given, you don't need to include the frictional forces here. Okay, so that is why here in the equations of motion, when you take the sum of all forces in x, you're only taking into consideration the force A, or the driving force of cart A, which is 40T. Alright, so that gives us 40T equals MA, okay, where M is the weight of all trucks, or the mass of all trucks, or the combined mass of all trucks rather, okay. And so we arrive at an equation for A, which is a function of time, 0.7256 T. Alright, so applying the kinematic equations, we know that acceleration is not constant, and therefore velocity is not constant. So we have to employ the differential equations, or the relations that we derived in the previous modules. Okay, so keeping in mind that v naught is equal to 0 at time t equals 0, so applying this differential equation relating a to velocity and integrating from 0 to 2, we have a velocity of 1.45 feet per second for the velocity or the speed in 2 seconds. Alright, so next we can determine the force between the truck and cart B by considering the free body diagram of the truck, so that we can expose the coupling force T as external to the free body diagram. So summing up forces in X will give you this equation here using the equation of motion. So since we already determined T as a function of time, which is necessary for which brings us to the point that we cannot just go ahead and apply this straight out of the box, we have 40 times 2 minus T, because 40 T is the force of driving force of truck A, okay, minus T times 900 over 32.2 times 0.7256 times 2, that's the acceleration, and solving for T will give you 39.4 pounds. Example M4.4, a smooth 2 kilogram collar is attached to a spring having a stiffness of 3 Newton per meter and an unstretched length of 0.75 meters. If the collar is released from rest at A, determine its acceleration and the normal force of the rod on the collar at the instant y is equal to 1 meter. So this is considering that the color drops from A to point C. Okay, so the steps that we will be taking here are only two. We will be drawing out the free body diagram of the color, because this is the idealized particle that is moving, right? And we will be applying the equations of motion from that, since we are not asked for the position or the velocity of the color at any time. Okay, so drawing out the free body diagram here, we see that the color at C is here applied is okay. Here applied is there is a force in the spring, Fs. So this force in the spring is always directed towards the other end of the spring. Okay, since if you imagine a rubber band, it will always when you stretch, there's always a resistance that will bring it back to its original position, and that is why that is so. Okay, so we have a normal force as well, since this is being pulled here, going into the pipe, right? Okay, we have a normal force here going into the pipe. We have a weight of the color since it's going downwards. We take the datum line to be here, so this will be y equals 0, and assume that a downward position is positive, or the downward direction is positive. All right, so I think we have everything there. Here in the free body diagram, you see exactly that, except that we have the addition of theta, where theta, okay, is dependent on the movement of the color, because it dictates the position of the color dictates the angle of inclination of this spring, which, if you apply the laws of geometry, these are opposite angles, and therefore they are equal. Okay, and so we have four unknowns, namely normal force, spring force, the acceleration, and theta. All right, so applying the equations of motion, we have nc plus fs cosine theta is equal to 0. I think you shouldn't be surprised why this is cosine theta, and we have for summation of forces in y, we have 19.62. That's positive because we take the downward direction as positive, minus fs, or the force in the spring, sine theta, is equal to 2a. This 2 is from the mass of the color. Okay, it's from the mass of the color. So from the equations of motion, it is seen that the acceleration depends on the magnitude and direction of the spring force. So solution for nc and na is possible once the force in the spring and the theta are known. Okay, so since the force in the spring is a function of the spring stiffness k and the deformation in the spring s, we can go ahead and solve for the force in the spring, right, in terms of y. Okay, so we have 3 times the square root of y squared plus 0.75 squared minus 0.75 squared. And where is this from? Well, we know that this is 0.75, so this is the original length, L sub naught. Okay, this is the final length, L. Okay, now relating this to this, we have relating this to y and this length, we have notice that we formed a right triangle, and therefore L squared is equal to L sub naught squared plus y squared. All right, and therefore since S is equal to L minus L sub naught, okay, we can find a way to we can find a way to solve S in terms of this equation here. Okay, so we have L squared. L squared is basically or L. Okay, L is basically the square root of L sub naught squared plus y squared. Okay, so plugging that in here, we have S is equal to the square root of L sub naught squared plus y squared, okay, minus L sub naught. And we know that L sub naught is 0.75, which is why we see here this is y squared plus 0.75 squared minus 0.75. Okay, I hope that's clear. Theta you can get in terms of y by trigonometry. So that is tangent theta. Tangent theta is y over 0.75. Alright. So since we specified, or the problem specified rather, that we determine its acceleration normal force of the rod on the collar at the instant y is equal to 1 meter, we can go ahead and plug in y as 1, and we can solve for theta, which will bring us to a theta of 53.1 degrees, while the force in the spring will be 1.5 newtons. So, plugging these values into the equations of motion here, we will be able to determine NC and A. Okay, so the normal force will come out to be 0.9 newtons, and the acceleration will be 9.21 meters per second squared downwards.